Yeah, Naveen is here. I can see you now. So you can go ahead and share your screen. So Naveen will be continuing the
Yeah, I
reads
can you
and
see my?
finite. Yeah. Okay. Thank you, Naveen. Continue.
Yeah, can you people see my slides?
Yes, we can see your
Ah.
slides.
So in pencil code, basically we solve the MST set of equations, and recently there has been development of look at even gravitational waves, other chemistry problems. Okay, but basically initially when it was developed, it was developed to look at these MST equations. So these MST equations basically describe the plasma settings which are there in the many astrophysical situations like sun, earth, galaxies. Almost all of them have turbulence and charged particles in them and magnetic field. So, uh, so when we want to solve any like partial differential equation, the main foundation that we have to set is what kind of differencing schemes that we use for the time and the space. Okay, and whatever schemes that we use, it has to be numerically stable. Otherwise, the solutions that we get, you know, will be sort of garbage, and it will never going to represent the real situation. So this is like the first one is the usual Navier-Stokes equation that you most of you might already know of. Okay, which basically describes the fluid motion acted upon by the various forces like pressure, viscous forces. This I have shown it for the very simple case like when the divergence of V is 0, and then there is a back reaction due to this magnetic fields, okay, which can act on this fluid and they can influence them. And then there is this continuity equation, which is basically tells that mass which is going through the any volume should be conserved. And then in the pencil code, we don't actually solve the induction equation. So we actually solve the vector potential equation. The reason is that for the vector potentials, the divergence of B condition could be satisfied very easily without any errors, rounding error, whatever we talked about. Okay. And if you look at these equations carefully, you can see that these equations are first order in time and at most second order in spatial derivative. This is a Laplacian, which is second order in space. And there's a current sitting here, which is curl of B, which is first order, and this is also first order, and time is also first order. So let's look at like spatial derivatives. Okay, in general, when we have to calculate the spatial derivatives, you know, the usual textbook schemes that we start off is from the Euler schemes. Okay, in Eulerian scheme, what we do is, if we want to calculate the derivative at certain point x, then we take the difference of the function at next step, which is x plus h, minus the value of the function at that point where we are taking the derivative, divided by the step length. Okay, and you can see that by making a Taylor expansion of f of x plus h, you can see that this Euler scheme is you know, accurate up to the order h. Okay, so order h schemes are not really good, and also this has very instability problem also in them. So the better would be to go for the central differencing schemes. So in central differencing schemes, what they do is, uh, you know, you have a function, let's say x plus h, you make a Taylor expansion like this. Okay, you have a first order derivative, second order derivative. Up till second order derivative only we look at. Then there is a error term which is of the third order, and then you make a Taylor expansion of x minus h, and then you will get the odd derivatives, signs will flip. Okay, when you subtract these second from the first, no, you can see that all the even terms, even derivative terms will just vanish. And you just do the little bit of algebra like f of x plus h minus f of x minus h, then this is like 2 times h. You'll get the error. This is h cube, but when you divide by h, you'll get h square. So this scheme is like, you know, accurate up to the order h square. The previous was up to the order h, but this is up to the order h square by just, you know, changing the way I calculate the derivative. And you can also calculate the second derivative in this by just adding both of them. Okay, so the first derivative will cancel out. So you have the second derivative. And here also you can see that the error term is of the order h square, better than the Euler scheme. Okay. But do we stop here? No, because we want accurate and accurate scheme. So graphically what is happening is, okay, let's say you have a function which is varying like this. Okay, you want to calculate a derivative at point A, which is actually a tangent, which is the slope of the tangent at the point A, right? So in the Euler scheme, what we used to do is, like, we used to approximate the slope of the function at the point A by this secant which is going from the A to B, right? And you can see from the graph itself that it is way off, right? On the other hand, if you look at the central difference scheme, what they do is they approximate the function by the secant which is going from the x minus h, okay, to x plus h. And you can see visually also that this is sort of producing better approximation to the slope at the point A. So that's why it has like less order of error compared to the Euler scheme. And you can actually improve the order even further. What you can do is you can take like finite differencing over twice the step, like from x2 to x minus 2 to x2, like from x minus 2h to x plus 2h. And then you'll get one more chord, and you use this chord in such a way that whatever error that is between this, slope of this chord and the tangent, you try to eliminate it to the next order. So the way they do is as the following. Like for the fourth order scheme, what you do is, like, you have, you already seen this. Okay, you have first derivative, and then you have the second order, uh, um, second order error, but there you will have the third order derivative, right? Which was, if you can go back, sorry, there was like third order derivative error, which becomes h square there. Now our focus is to try to eliminate this term. So now you do the same thing with twice the steps, okay? Then you will get something like this, which h replaced by 2h. And then you add and you weight it appropriately so that this term gets cancelled, okay? And this is the weighting. So if you multiply this by 8 and then do the subtraction, okay, you can get rid of this third derivative. And this scheme is accurate up to the order fourth. And second derivative also you can express like this. And you can, I mean, still go on higher. You can like take 3 function evaluation on the left and 3 function evaluation on the right. Then you can get the accuracy up to the order 6, okay? And this is what is done in the pencil code. This is explicit schemes, okay? All the derivatives, like first derivatives and second derivatives, are calculated up to the order h6. That is like way too accurate. So now you can ask, like, we generally solve the problem in a computation grid, right? On a discrete grid. When you're on the boundary, what happens is that you need the information of 3 more points which are away from this boundary. If you look at this equation, like, if this is f of I, then you require information of -1, -2, -3. So generally, it's a normal practice that you define 3 more points across your grid points, which are called as a ghost zones, okay? So because this is a 6th order scheme, you require 3 on the right and 3 on the left. There are total like 6 ghost points. So whatever, like if you're running 128 cube simulation, then including the ghost zone, it will be like 132. So 132, I mean, this like 6 points, like 3 on this side, 3 on this side, is used to store the boundary conditions, right? And that could be used to calculate the derivative at this point. This is just for one single processor. Let's say when you parallelize the scheme on many processors, what happens is you cannot add boundary, this ghost zones in between 2 processors, right? So what they usually done is the information on the other processor itself up to the first 3 point is used as a ghost zone. So at every time step, to calculate the derivatives at the boundary of the one processor, the code has to be written in such a way that one has to communicate these values which are at this boundary to this processor X at each time step, okay? And I thought I'll explain these indices because in this pencil code, These indices are like a global variable which are stored. Okay, so my is the length of the uh, points in the y direction. Okay, including the go zone. These things maybe you need it if you want to really modify the code and make a modification. Probably I will not get into this. Maybe when Philip explains more about the pencil, cache efficiency thing, then maybe this is useful. So now the next thing is the time stepping. Okay, till here, if anybody has a question, they can ask.
So yeah, so if there are questions.
Yes, so I have a question.
Yes.
Go ahead.
So when on the slide where you were talking about the ghost zone,
Yeah.
and when you are communicating from one processor to another processor,
Hmm.
so the ghost boundary is common between the two processors, right? The actual data values are not used as the ghost zone for the second processor.
No, no, no. They see that for example, this for the X processor, okay, there is already some value on the neighboring processor, and those 3 points is treated as a ghost zone for this particular processor, but not for this neighboring processor. For this thing, this is just a normal points. For this processor, 3 points on this processor is treated as a ghost zone.
So the ghost zone values, the values which are used into calculation in the ghost zone,
Hmm.
I mean those are actual data values or some
No, they are actual
artificially
data
created
values.
values.
They are
Okay.
actual data values which are there on the processor. Only at the last processor, okay, when you are like at the edge, those 3 points, like 3 ghost zones are there. That is not part of the computation grid. That's it. But
Okay.
rest of the ghost zone, which are across like around the processors, they are part of the computation grid.
Okay.
We just treat it that way. That's it. Because to calculate the derivatives, because as you saw
Mhm.
that we require if you want to calculate the derivative at the boundary where the
Mhm.
processor ends here, you need extra 3 more points.
Right.
So that information has to come from the neighboring processor, and that is actual points, actual velocity field, magnetic fields.
Yeah. So that I understood that i- if suppose in the x direction I have 128 pixels and in y direction I have 128 pixels.
Hmm,
So
hmm.
at the boundary, if I have to make the calculation, I need three additional points on the
Either side.
out of that boundary.
Yes,
So from where how do I input those values for the ghost zone? Because that is not actual velocity and magnetic field.
that is initially you calculate it, okay, using some, you always, this is the initial value problem that you're trying to solve. So there is always some initial condition that you give, velocity field and magnetic field, okay, and after the certain time, even those ghost zone values are updated.
Right.
So then it is used again. You getting it? Initially, it is just the initial values of the velocity field and the magnetic field.
Mm-hmm.
Okay, you iterate it and go to the next time step, and after you calculate it, uh, in the grid you will change the velocity field and magnetic field will change. Then you change also the ghost zone values,
So
update the ghost zones, and then you
ghost
will
zone
calculate.
values are actual velocity and magnetic field values, right?
Yes.
Nothing artificial.
Yeah, but only thing is the derivatives are not calculated there. That's it in the ghost zone. That's all it means.
Okay.
You only stop here.
Mhm.
That's it.
Right.
Because you, if you want to calculate derivative in the ghost zone, then you need 3 more. Right?
Mm-hmm.
It can go on like that.
Okay. Okay.
There are host zones between processors which are actually real points.
Yes.
So like you said, you gave this example of 128 by 128 pixels, right? So if that is, if you have to solve your equations on 128 by 128 on a particular processor, which is in the middle of this, say this X, marked X on Naveen's screen. So then that processor will actually store 131 by 131, right?
Okay.
So where these all these 6 grid points are being exchanged. So that is coming from the communication, like Naveen was pointing out. The processors also have to communicate.
All
right?
right, all right.
Yeah.
So
And
those
also
are
one
not real ghost zones, but they are, internal ghost zones. But the real or the actual ghost zone is in the boundary of the actual domain, whose size may be larger than 128 by 120 in your
And also
case.
one more point, in pencil code, all these schemes are like explicit schemes. Okay. For the implicit schemes, you have to solve kind of a tridiagonal matrix, and that is an iterative process. So for each time step, you need to iterate it for some 10 or 20 steps, and for each of those 20 steps, you need to keep communicating with the neighboring processor. And communication is a time-consuming process. Okay, so it will really slow the code. So if you want to really run the system on really big, processors number, okay, the explicit schemes are the way to go. If you have, let's say, a kind of a system where you have just one memory and processors attached to it, then for them implicit schemes are okay. But actual main parallel processing units are like, there are like processing unit, you will have a memory, then there is a processing unit like nodes, you have a memory. In such a situation, the explicit schemes are better. But if just one memory is shared to all the processor, in them the implicit schemes are okay. So, but in pencil codes, we always use the explicit schemes, because the idea is to like, scale up to the any number of processors. Okay.
Okay, okay.
So I'll go to the next, like time stepping. So in pencil code, we use something called the RK method, Runge-Kutta method. You must have heard of this method in numerical classes everywhere. So they are very robust methods. Okay, and even like if you look at the Python routine or the usual numerical recipes of the Fortran F90, this numerical recipe book that usually people refer to, the OD int there also uses RK4, Runge-Kutta method of the order 4. So we look at what is this order 4, order 3, or order 2 methods are. Okay. So now when you looked at those equations, okay, all those equations you can put it in this format. Like now, like I have finished the time derivative part, sorry, the spatial derivatives. Now I'm going to the time step. So we'll just focus on the just time stepping part. Okay, the first, because these are all the first order in time, so you can cast all of the equation in this form, like dou u by dou t equal to f of. Generally in this fluid equation, it is not a function of t, but it's a function of u dash, u double prime. Okay, derivatives, but whatever. This is the simplest thing. So now u could be scalar, or it could be hold number of variables like velocity field, magnetic fields, and density and other things. So let's just look at just one dimensional case, scalar case, simplest to understand it. Okay. So the normal way to propagate the solution from the time t0 to t1 is, as usual, like use the Eulerian scheme. That is the standard. Okay. When you do that, it's just a Taylor expansion of this. The velocity field at the point t1 as expressed as the velocity point at t0 times the space length multiplied by the derivative of the dou u by dou t, right? Then this scheme is accurate up to only order h, that's it. Now, if you have studied like mathematics, there is something called the mean value theorem. In mean value theorem, let's say, you have like curve which is going between the 2 points, t1 and t0, and you take the difference of the value of the velocity field at point t1 and t0 and divide by the step length. It will give you some slope which is connecting this, which is the secant slope, right? If the curve is passing through that, then by the continuity and the differentiability condition of this curve, if it is differentiable, then you are guaranteed to find a slope to this curve at some point xi, such that it is exactly equal to the slope of the secant, right? That is the definition of the mean value theorem. And now you can express like u of I plus the velocity field at t1 in terms of velocity field at t0 plus h times the value of that slope. Here the slope is like u dash, which is f, okay, evaluated at a particular point. And this is exact, okay, there is no approximation here. And this is accurate up to infinite order with just one function evaluation. So the difference between the Euler scheme and this mean value theorem is that you have moved the function evaluation from the initial point t naught to somewhere in between your time step. Okay, and just because you have moved your evaluation, you have acquired the accuracy up to the infinite order, actually, theoretically, of course. But can I really calculate this f of this this slope at this particular point? If I ask that question, then normally, so to know this function f, you have to know the velocity at that point u, at the point xi, right? Then I can apply the same mean value theorem for this u of xi. So when you do that, u of xi, you can write it as a velocity field at time t naught, and then the h, here the time step is different because now we have to look at xi minus t naught. It is not xi1, xi minus t naught. Then you have to choose some slope at some intermediate point xi1, okay, which will match the slope of this secant going from t naught to xi. And then you can actually regress this. To again find the value of the velocity field at xi1, you need to find the slope value at somewhere in between. And you can immediately see that to calculate the slope at this point, you need to know the slope at the infinite points to get that infinite accuracy, right? Accuracy up to the infinite order, which is, I mean, numerically it's not possible. So what Rung and Kutta did was, like, instead of, okay, this particular function, it's a slope at this particular point, right? You can actually equate it to the slope, weighted average of the slope at different points. That you can always do, right? A phi number could be expressed in terms of 3 to 1, sorry, 3 plus 2, something like that. So the slope at the point xi, you could express as number of slopes, okay, weighted average of the slopes at different points, xi is, let's say. And how many number of slopes I should take, that decided by the order of the accuracy that I require. So generally, the number of slopes are, indicated by the stages. Like S stages means there are like S slopes I'm going to take. And then just take the weighted average of that. So for the second order scheme, for the second order Runge-Kutta scheme, I just require 2 slopes. Okay, the slope at the point at initial time t naught and somewhere in between. And then for the third order scheme, I require the slopes at the 3 points, k1, k2, k3, okay, all in between. And for the fourth order, you require 4 slopes. Till fourth order, you require only 4 slopes. But if you want to calculate the fifth order, you require actually 7 slopes. And this, the 2 times the increase will go on till, ninth order. When I was preparing for the lecture, I was just reading about it. And somebody has gone up to the 9th order Runge-Kutta method, and they require something like 16 to 17 slopes. Okay, the linear scaling is only up to the 4th order. That's why in most of the schemes you just stop at the Runge-Kutta order 4. That's it. Because even to calculate the order 5, you require 7 slopes actually. You can't do with 5 or 6. Okay. So now for the second order accuracy schemes, okay, we are using the 2 slopes. That is the slope k1 at the initial point, and then the k2, when I have calculating the k2, this is the crucial step here. So this is calculated at some intermediate time, alpha 2 times h, where alpha 2 is less than 1, okay, and the velocity field is actually calculated at that particular time step, and that velocity field is only expressed up to the order h, because this is second order. I need only up to order h in this place, and it is again the same process that is applied here. The velocity field here I have used 2 slopes, okay, to express here. The velocity at the the intermediate point I have used only 1 slope to approximate. So for the third order, this you will do it iteratively. Like you calculate the slope at the first, and the second slope you calculate some intermediate point, and the velocity field, when you have to calculate that slope, you will use previous slope, okay, which is accurate only up to the order h. Then for the third slope, what you do is you use the previous two slopes. So this is order accuracy up to the order h square. Okay, so totally it will give you the third order accuracy. So now I'll just show you the brief derivation for the second order, how to, these are all the free parameters, coefficients, okay, there are like 4 parameters here. And for the third order, there are like 8 parameters. And for fourth order, it will go up like 13 or something, 13 or 14. So even just one order increase, the amount of computation that you have to do goes like exponential. So generally what you have to do to find out these coefficients is, one of the advantage of the Runge-Kutta method is to get the higher order accuracy, okay. Nowhere you have evaluated any higher order derivative. It's just that you're evaluating the function at different points within the time step to get the higher order accuracy. So if you just see this derivation, you'll understand why that is the case. Okay, so now you have the dou u by dou t times this, you integrate this, okay, over this time step t naught to t plus h. So this f of t comma u, you know, uh, use the Taylor series to expand up to the order first order. So this you need to take the time derivative. So you apply the chain rule. The first derivative is like dou f by dou t plus f. So just bear with me. Just I'll finish this. Okay, I know it is a bit of calculation. So then with the chain rule, you do this like dou f by dou u. Then dou u by dou t will give you the f, right? So when you integrate this, you will get the h here. So this will become h square, and this will become h cube. So you have now expressed u of t up to the order h square using the Taylor series. Now you have this k2, right? The previous, you have this k2. You make an expansion of k2 up to order h, first order. So that is just this f of at the initial time, and then first derivative of the time, and then the first derivative of f with respect to the u. And this is the delta y sort of d2hf, and this is delta x. And when you make the comparison between, you know, and you just use this expression, sorry, where did I go? Just substitute this into this previous expression. Then you will get like the conditions for the omega 1 and omega 2, which is like omega 1 plus omega 2 is 1, and this alpha beta should be equal to, should be same. And then alpha omega 2 should be half. Okay, and you can see that this is accurate up to the order 2, like h square. You can get infinite schemes by just playing with these numbers. But the only thing is you shouldn't choose omega 2 equal to 0, because otherwise you are killing this order and it is not accurate up to the h square, right? So traditionally the people use like omega 2 is equal to h, then alpha will become half. Then you're evaluating the slope at the initial time and then at the intermediate time. This is also called the midpoint method, right? And then if you just choose the variables slightly differently, the omega 2 is equal to half, then alpha becomes 1. Alpha is the time step, how much far I should evaluate the slope at. So then the k1, that is always default, so you are evaluating at the time t naught. Then you are evaluating it here actually at the end of the time. Okay. So these are all just two variants. In the third order scheme, you know, as we saw in the second order, there are many variations that are possible, right? So in the third order Runge-Kutta, you have 3 stages, meaning you require 3 slope evaluation, one at the initial, one at the midpoint, and then at the last. So when you are trying to, so there are like 3 storage values that you have to use for each time step, right? If there are m equations, then you have to store 3m values. And if there are n points in your grid, then so many points you have to store. So for example, if you're running the 512 cube simulation, okay, and you are running on double precision, so one number will take like 8 bit. So that 8 times that 1 bit will take like 1 GB, 1.07 GB of the space for just one variable. Okay, one value of storage. Then you have, let's say for the 6 variables, the 3 for the velocity and 3 for the magnetic field. And then for the 6 variables, you require like 6.4 GB of storage. But to calculate this RK3 method, you require 3 storage value. So 3 times this will give you like 19.3 GB of RAM you require, if you want to run minimum. Just for this, if there are like other equations, entropy, chemistry, other things, then this will even increase further. So next people thought like, can we put this, the stage evaluation is, fixed. You can't change that. But can we put it in a low storage format? And those are all the schemes called low storage Runge-Kutta method. So not all schemes, for example, I'm talking about the third order. So not all third order schemes can be put in 2 storage format. Okay, only certain, for example, the previous schemes cannot be put in the third order format. This one, okay. But if you slightly make a modification to that scheme, by killing K2 and then change the slope value a little bit, that again you have to do it consistently, then you can put this in this format. Okay. This alpha 1 is 0 for the first variable, so this is just this hk1. You store it in omega 1, then use that omega 1 to calculate the vi. This is u0. Okay. Then you, for the next iteration, you just use this here and replace the previous value. That's it. And for third stage Runge-Kutta, we have to run the loop for 3 times, but I have to store the values only in W and V. And these types of schemes are called 2N RK3 scheme, and this is exactly what is used in the pencil code. Okay. So why till very recently the RK4 was not used, because for the 4-stage fourth order Runge-Kutta method, you require 4 stages, meaning 4 slopes that could not be put in this 2 storage format. It could be put only in the 3N format. Then I think last year it was coded in, where somebody had developed a scheme where you can calculate the Runge-Kutta method to the order 4, but with 5 stages, like means the 5 slopes that could be put in the 2N storage format. Okay. So I'll just show. Anyone has questions still on? Hello. I'll just show the. Can you people hear me? Okay, I'm not getting any response. So I'll just
yes, we can hear.
Oh, okay. So I'll just show this. No, I came out of this. So this is the source code directory of the pencil code, okay? And you have all this like time stepping schemes here, different time stepping schemes. The basic one that is used is this timestep.f90. So let's just look at this file. So here, okay, you can just read it off by yourself. So these are all the key tags that were used, like IT order 1. If you, there are certain files called run.in file. Maybe later in this week, if somebody is like showing you how to install pencil code, they'll tell you about, there are input files like run.in, print.in and all. So in the run.in file, if you just say IT order 1, then it will just take the first order Euler scheme. If you say the IT order 2, then it will take the second order scheme. IT order 3 is what the Runge-Kutta 3 method that I discussed about, okay, the 2 storage format that will be used in the code. And this is the IT order 5. There is no 4 here because this IT order refers to the number of stages, number of slopes that are used. And you can see here, I mean, this, I'm just showing you one file because the code is extremely, commented everywhere. You can just, if you know certain numerical skill basics very well, you can just go and read it yourself. Like you can see this is a Runge-Kutta time advance, accurate to order, IT order. So only up to 1, 2, 3 orders were there. Last year, somebody added the 2N RK4 coefficients, and you can read it here. The coefficients are for the 4th order. but use 5 stages, because I told you the only 5 stages to be put in this 2 in storage format. Okay. Yeah. So the next in the this thing is like stability analysis. I could very well stop here if you people are tired to listening. I can take it up at next time and next tutorial. Or else I can
Maybe
continue.
you can go on till 7 or something.
Okay, fine. Then I will just finish off it. Okay, this I don't know. So now the next thing is you have like you have like now we know like for a given fixed delta t, we need to make like slope evaluation like twice, thrice, or four times, 5 times, right? So now the next question is how much delta t I should take. So if I choose the delta t really small, then the cost will, the computation cost will increase like huge, right? Because at each delta t I have to make 3-4 slopes evaluation. And if you take delta t to be really large, then it will lead to sort of an inaccuracies. So is there an optimal way to decide what delta t you should choose, sort of making it an adaptive time stepping? Okay. So that is decided by your stability of the difference equation. So you should only take the delta t up to that point where your stability criteria are. So to understand that, we need to look at this von Neumann stability analysis. Basically, what this is, just a discrete version of the stability analysis of the continuous equations that we make. So I'm just taking the transport equation here, just a simple format. Dou u by dou t is equal to minus v dou u by dou x. So this you can see that it will all arrive in the Navier-Stokes equation. It will also come in continuity equation. It will also come in the magnetic field equation, right? This kind of a form, dou u by dou t times v. So this is very generic form in the fluid equation. So if you want to study the stability of any particular equation, in the usual sense, in the continuous case, what you do is you just take the Fourier mode and then multiply e power gamma t, okay, and look for the case if the gamma, e power gamma is greater than 1, then it will lead to the instabilities, right? If it is less than 1, then the system is linearly stable. So this is just a linear stability analysis on that. So now in the difference scheme, what we do is we need to take the discrete Fourier transform modes because it is not continuous, because my grid is now discrete, right? So the grid is the x, j is discretized with j varying from 0 to n. The n could be 128, 512, whatever, okay? Then n is also discretized. And then I just label the velocity u, time tn and xj has, top indices is the time, the bottom indices is the space. Okay, now I'll take this equation, the simple advection equation, and then I'll use just the forward time and the central differencing scheme for the space. So this is just the Euler scheme. Okay, the time at n is related to the like time at n plus 1. But here this is the central difference scheme for the derivative, which I just mentioned at the first of the lecture, where I'm taking the value at j minus 1 and j plus 1, like x minus h and x plus h. Okay, and this is explicit in time scheme. So now I'll take the Fourier mode in the discrete mode, okay, with xi of n e power I k j delta x. If xi is greater than 1, when I substitute in this, and if I find out that the xi is greater than 1, then it will lead to the instability. If xi is smaller than 1, then it means that this numerical scheme, whatever I have used, is stable. I have to make sure first. This is true for all explicit schemes, whatever explicit schemes you choose. And implicit schemes we can't choose because it is not easily parallelizable. So for any explicit scheme you choose, you should first make a stability analysis and then only implement it. Okay, for the simple case, okay, so just be with me with this calculation for some time. U of like n plus 1 j, you could express as this, right? you just substitute, then this n plus 1, this I will come out. And then you need j plus 1. So that could be written as e power I k delta x u times nj. And this is, you will get the minus here. So when you substitute this in this Euler advection difference equation, you will get psi as 1 minus I v delta t. This will give you the sign. Okay, e power I k delta x, e power minus I k delta x by 2 delta x. So this will give you sine delta x. Okay. So now let's look at what is this k delta x first. So k in a discrete Fourier transform, you know that it is just 2 pi by L times n, where n is going from 0 to n minus 1. If there are like n discrete points, then this index can go up to like n minus 1. So now delta x, you know, because this is like the length of the box divided by the number of points that you're choosing. So k delta x is nothing but 2 pi n by L. So you can see that the k delta x only varies from 0 to 2 pi, right? It's like an angle theta, you can treat it as. So that was the goal of showing this thing. So you can treat this as a theta, and you can plot this xi in an organd plane, like in the complex plane, to make a stability analysis. So you know that for the stability of the equation, you require this condition, xi should be less than 1. So in the complex plane, that is just a circle. And whatever scheme xi you calculate for any scheme, that should be within that circle. So for example, for that particular case, when v delta t by delta x is 0.5, and this is the stability. I mean, the xi is 1 at this boundary, and this is inside this region is the stability region. Okay, but for this particular scheme, so this is the real part and this is the imaginary part. Real part is always 1. Okay, so you'll just get a line. So you're already outside this boundary region. No matter what v delta t by delta x you choose, okay, you're always outside. So this is unconditionally unstable scheme, the Euler scheme. Okay, you cannot use it. It is good for textbook case, but never for the serious numerics. So now the trick is, can we make this table? So instead of unj, you substitute the average value taken at j plus 1 and j minus 1. Okay, this is called the lax method. This thing is there in numerical recipes. You can see that. So when you use that in this, in place of un of j, so now you make a stability analysis. So now instead of 1, you will get a cos k delta x here. Okay, this makes a lot of difference now. Then you have same term here. Now this is the like your stability region in the organd plane, in the complex plane. Okay. Now if you choose the v delta t by delta x is 0.5, let's say, okay, when this cos 0 is, when cos is 0, it is 1, right? You are on the right side. When cos of pi, when this is pi, you will on the minus pi. So the real will go from -1 to +1. And then if depending on this value, you will, this like ellipse can like grow bigger or smaller. So for v delta t by delta x is 0.5, this is within this region. See, just by changing this scheme a little bit, you made this like numerical scheme stable. Like xi is now less than 1 for this v delta t by delta x. But if we choose v delta t by delta x more than 1, then it will go outside this region of your stability. Then it's again unstable. So the stability criteria is that v delta t by delta x should be less than 1. Okay. So this is traditionally known as the Courant-Friedrich-Levy stability criteria. So this was this or simply they call it as Courant condition. So these people wrote about this in 1928, I guess. Okay. So what this physically means is, let's say you have a grid space of delta x, okay, and you have a delta t time, and then there is a velocity, okay. So in a delta t time, you are going to move in this grid up to the distance v delta t, let's say up to here. So when this is less than 1, you are not going to cross this delta x. On the other hand, if your delta t is really large, okay, then you could easily cross the length of this grid. and your analysis says that whenever this is more than 1, it leads to the instability. And whenever, so it's sort of a physical thing, you cannot transport the fluid in a given delta time more than that grid spacing that is allowed. So whatever advection that you do, it has to be within the delta x. Only then your numerical schemes are stable. Okay. So now, if you want to physically understand what is this lax method is doing, so you can put that equation, this equation in a forward time central differencing format. So you just multiply u and j on both sides. Sorry, subtract it on the both sides. If you, sorry, where did I go? Here. I'm sorry. So subtract it on the both side. U of n j here and here. Okay. Then this is, if in the continuous limit, you will find that this is dou u by dou t, and this is just v dou u by dou s. So this is nothing but a second derivative, right? And with this diffusion coefficient, and this leads to actually the numerical viscosity. So what it is doing, this lax method is, let's say if you take the Fourier analysis, this is like k square, k delta x, right? So for k delta x, which are equal to 1 around, so it is damping all those modes. Okay. For k delta x, which is smaller than 1, which is the large scale modes, are not damped, but the small scale modes are actually damped, because that was the one which was leading to the instability. You can see here previously in the first method, forward time center difference scheme. Okay, where is the stability? Here. So this, whenever, like when k delta x is very much smaller than 1, this is almost 0, right? So this is equal to 1. So for large scale modes, there is marginal stability, near to the marginal stability, not exactly stability. But for k delta x equal to 1, for the small scale modes, this scheme is unstable. So what lax method did was, it introduced a numerical diffusion to kill that instability at the small scale, right? So this kind of schemes are called non-conservative schemes. Okay, either this kind of a numerical viscosity can come because of these numerical schemes, or it could come because one would introduce it artificially. So in pencil code, all like equations are like in non-conservative format in these schemes, either because they have added numerical viscosity by hand, or because of the schemes that I have used, there is already a numerical viscosity that appears. Okay. And then let me just talk about the upwinding. This is just the last slide, last but one. Another maybe 5-10 minutes, I'm done. So now, okay, this equation had solved first order in time and second order in space. Okay, let's say I will just do this first order in space. So in the lax method, what was happening was, so what was happening was, you had transported the fluid from J to n plus 1, okay? Then you had said you will take the, instead of taking the value of velocity at here, you said that you will take the average of the velocity at here and here, right? For the next time step, what is happening is, you're actually transporting the fluid element from both the directions, from Z plus 1 to Z, sorry, from J plus 1 to J, and from J minus 1 to J. But if you physically think of, okay, when the velocity is positive, then the fluid should go from J minus 1 to J, right? When the velocity is negative, then the fluid should go from J plus 1 to J. So it depends on the sign of the velocity field. But this previous scheme was, it was just taking the, fluid element from both of the points to that J, whether it V is positive or negative. So if you make that correction, if you allow that physical insight into your numerical scheme, okay, you can see that you can actually achieve much better stability. This kind of schemes are called the upwind differencing schemes. Okay, so now when the velocity is positive, you know that only from J minus 1 the fluid can go to J, right? So you write it in this fashion. And then when the velocity is negative, so it should go from J plus 1 to J. right, in the opposite direction. So you write for the velocity negative in this fashion. Now we make a stability analysis. Okay, I won't bore you with the details, but you can see that you will get something of this format. And this is for the velocity greater than 0, and this is for the velocity less than 0. And if you just carefully look at, this is the real part, and this is always positive, right? And this is negative here. The moment the v becomes negative, this becomes 1 plus v, and you can see that it becomes unstable, right? And the same is true for the other case. Like here you get cos k delta x minus 1. So this is always negative, so this is plus, so this is stable only for v less than 0. The moment you have v positive, this becomes like unstable. So use these if conditions in the code and like to calculate the difference. You just here, this is both first order in time and first order in space. You can actually increase the ordering of the space by having this j minus 1, j minus 2, j minus 3 like this. Okay, in pencil code it is done up to order 6 in this direction, and for the other velocity field it is done in this direction, like j plus 1, j plus 2, j plus 3 like that. And this is just a organ diagram for that scheme. Okay, when you have v delta t by delta x is in the 0.1, this is the circle you will get, which is well within the stability region. The moment you have v delta x times like this thing greater than 1, it will go outside the stability region and becomes unstable. Again, you will get the same condition. Okay, but this has to be followed, like this convention. Now, so you saw that here, do we always get the same kind of Courant condition? No, that depends on because I had considered the advection equation. So whatever scheme I had used, I always got this as my stability criteria. If you look at the diffusion equation, let's say, which is first order in time and the second order in space, you can again do the same stability analysis, and you can find that this is the stability criteria. And we can understand this like the diffusion time scale over a grid delta x is given by this delta x square by d. So that is the time it takes for the fluid or passive scalar or whatever, some concentration to diffuse across that length delta x grid size. And I should choose my delta t which is smaller than this tau by 4, right? It should be like the size of the delta t that I choose, it should be smaller than the diffusion time that is needed to cross the one grid. So now in pencil code, you have the advection term, one condition is coming, Courant condition. You have the diffusion term, there is one Courant condition. There are like entropy equations other, and there are other Courant conditions. So what you do, you take the minimum of all of them, the minimum delta t. And also, because your velocity fields are changing, okay, everywhere, you take the maximum velocity field, right? So for the maximum velocity field, you require the smaller delta t for the whole grid. So the Courant condition is actually a grid dependent quantity because the velocity field is a grid dependent quantity. Okay, so you take the minimum for whole of the grid. So in pencil code, you have something called this name called CDT, which will control this advection Courant time. CDTV, which is the diffusion Courant time. So I'll just show you in the pencil code manual. Okay, you can see here. So like default value of the CDT is 0.9. Okay, this is the Courant condition for the advective time step. And CDT is the Courant coefficient for the diffusive time step, which is like 0.25. You also have a provision to choose the fixed time step also in the pencil code, okay, which will override this Courant time step, but this is not advisable because you don't know when you are going to blow up the solution, or even if the simulation runs, let's say, at some of the times your Courant conditions are violated and you will going to gather some garbage. It is always advisable not to use the fixed time. Let the code calculate the time step at every time depending on the velocity fields and the diffusion coefficient. So I'll just summarize. Okay. Yeah, so in pencil code, we use like sixth order central differential scheme for the spatial derivatives. And for the time, we use like RK, Runge-Kutta method order 1, order 2, order 3. But recently, even Runge-Kutta order 4 was also added. And that you can access using the this name IT order 5, because it is a 5-stage scheme. And it's like we require like 6 ghost zones to store the the function value so that we can calculate the derivatives at the boundaries. And time stepping here is determined by the Courant number basically. Okay. And for different times, if there are different Courant conditions, then you can choose the minimum of that. And in the pencil code, you have this different time steps. Okay, you can actually call them. For example, let's look at the time step. Okay, so 10 or something. So this is again based on the Runge-Kutta, but then there is some Chebyshev, even I don't understand this, but what they're basically doing is they're trying to increase the Courant number. Okay. This is just a second order scheme, stage 2. Second order scheme with 10-step Runge-Kutta, but the idea of the using other thing is whatever method, this is the explicit scheme, whatever method people develop, it is all based on this Runge-Kutta, just variant of it. Either they're trying to increase the storage efficiency or they're trying to increase the Courant number so that you can take a larger time step. There are like many time steppings that are there here, and one can call them in the makefile.local. Wait, let me go to the any particular runs. I'm not used it anywhere, but I'll just show you that where to call the time step. So there is something called the makefile.local. You go here and you just say the time step. Let's say if you want to use a time step, some RKC10. Okay, you can just write it like this. And there is something called RKF, which is the Frederick variation over the Runge-Kutta method, which is generally used in ODE int, that you can call it like this. Okay. And derivatives also. I mentioned that in pencil code they use up to 6th order. Okay, but one can go up to 9th, 7th, 8th, 9th, and 10th order also. So you can also call them using derive is equal to something like derive. I forgot on the keys. I think derive 10, something like this, or derivative 10, I guess. But later in the other tutorials we could clarify. But if you use different, if you want to use different time step and derivatives, this is the file you need to look at. Okay.
You have to make sure that the file exists in the, or like there has to be second order is also there, for example, second order, fourth order.